Hello everybody. This episode, I'll be speaking with Adam Shai and Paul Riechers, who are co-founders of Simplex. Simplex is a new organization that takes a physics of information perspective on interpretability, aiming to build a rigorous foundation for AI safety. Paul has a background in theoretical physics and computational mechanics, while Adam has a background in computational and experimental neuroscience. For links to what we're discussing, you can check the description of the episode, and a transcript is available at axrp.net. Well, Paul and Adam, welcome to Axrp.
Yeah, thanks for having us.
Yeah, thank you.
So you guys work on doing computational mechanics for AI safety type things. What is computational mechanics?
So I'm happy to give a bit of a background of computational mechanics is basically grown within the field of physics, mostly out of chaos theory, information theory. For what purpose? Well, I mean, physics has always been concerned with prediction, that we want to write down some equations that tell us, maybe if we know the state of the world, what does that imply for the future? Some planets move around and all these things. And then there became a pretty serious challenge to that, being able to predict physical systems that came from chaos theory, where even if you have deterministic equations of motion, there's kind of a finite horizon to how much you can predict. And so I don't know if I'd say that physics was thrown into turmoil, but it was a serious challenge for what are the limits of predictability, and how would you go about doing that prediction as well as possible. So I'd say that's kind of the history out of which computational mechanics has grown. And so it's now a very diverse set of results and ideas, way of thinking about things and dynamics, but really at its core is, what does it mean to predict the future as well as possible? As part of that, what does it mean to generate dynamics, and how is generating different than predicting? If you have some generative structure, is it harder to predict? A lot of this stuff's been quantified, and a lot of the work that's been done is at this kind of this ultimate limit of what's possible. But there's also a lot of work that's been done, and more work now of if you have some resource constraints, then what does that imply for your ability to predict? And you're not asking yet, but I'd also be happy to share how that's relevant to AI ML. I'll maybe just throw it in there.
Sure.
That maybe this is obvious to listeners, but we're now training these AI models to predict future tokens from past tokens as well as possible. And while people are kind of poking around trying to understand what's going on, there's this theory that was developed specifically to address that. And so a lot of the mathematical framework maps on kind of surprisingly easy, where we've been able to come away with some results that we've been just actually surprised that it worked out so well. And it's a great framework to then build upon. I wouldn't say computational mechanics is the answer to understanding all of interpretability and AI safety, but it's really a great foundation and something that helps us to make better questions and see where research should go.
Sure. So I guess a bit more specifically, if I hear this pitch of like, oh yeah, we're interested in understanding how to predict the future as well as possible, someone might think, hey, that's Bayesian statistics. We got Bayes' theorem like 100 years ago. What else is there? I'm sure there's more, but what is it?
What are you doing Bayesian inference over?
Yeah, I don't know, stuff. You're gonna have some prior, and you're gonna have some likelihood, and then you're just done. What else is there?
No, exactly. That's I think that's my point. Is computational mechanics helps us to understand what are the things that you're trying to do updates over, and I think there's some question of from the start. I'm saying, okay, we're applying this theory because models are predicting the future as well as possible. But actually what we're doing is we're training them on this next token cross-entropy loss, right? Well, what does that mean? People have argued, right, about whether they can have some world model, and it's unclear what people even mean by a world model, or if they're stochastic parrots, and it's not even clear what people mean by that. So one of the advantages is that let's just take this seriously of what are the implications of doing well at next token prediction. And there's a theorem. It's actually a corollary from a paper from, I think, 2001 from Shai and Crutchfield, which, if you translate it into kind of modern language, says that to do as well as possible at next token prediction implies that you actually predict the entire future as well as possible. So then computational mechanics comes into play. And right, so I should say, yeah, it's more than Bayesian inference because what? Well, you want to know what about the past you need to predict the future. And, it would be, if you had no resource limitations, you can just hang on to all of the past. And there would be maybe a mapping from this past to this future. But with, some number of your token alphabet, the size of the number of paths would be growing exponentially with longer length paths, right? And so that's intractable. You somehow need to compress the past. And what about the past should be coarse-grained? Basically, there's kind of this obvious mantra, but when you take it seriously, again, it has interesting mathematical implications that for the purpose of prediction, just don't distinguish paths that don't distinguish themselves for the purpose of prediction. So that means if a past induces the same probability distribution over the entire future, then just clump those paths together. And also, if you want to say about lossy prediction, then you can look in that space of probability distributions over the future, and you can see kind of what histories are nearby in that space.
Sure. So can I, maybe a thing that would help my understanding is if I just say what I've gathered, kind of the interesting objects, interesting like things in computational mechanics are, and you can tell me like where I'm wrong, or perhaps more likely what interesting things I'm missing. Does that sound good?
Yeah.
Cool. Here's what I see computational mechanics is doing, just from a brief glance. It seems like it's really interested in stochastic processes. So it's kind of like time series inference of, a bunch of things happen at like, you've got this thing and then the next thing and then the next thing and then the next thing, and you want to predict the future. As opposed to like forms of Bayesian inference where like you're inferring the like correct neural network that's underlying this IID, this independent identically distributed thing, as opposed to, various other things you could do with Bayesian inference. And in particular, it's interested in hidden Markov models. Like I see a lot of use of hidden Markov models where basically there's some set of states that the underlying, there's some like underlying thing. The underlying thing is like transitioning from state to state in some kind of lawful way. And these transitions are associated with like emitting, a thing that you can see. Each time a transition happens, you like see a thing emitted. And basically, in order to do well at predicting, you've got to understand the underlying hidden Markov model, understand like what state is the hidden Markov model in. And if you could understand what state the hidden Markov model was in, then you do a really good job of prediction. Mm. I then see this construction of a thing called an epsilon machine, which, as far as I can tell, is kind of the ideal hidden Markov model of a certain stochastic process, where basically the states of the epsilon machine are just like somehow the sufficient statistics, like you were saying, grouping together all pasts that lead to the same future things. That's like just the states in the epsilon machine, and there's some sort of minimality of like once you have those are like precisely the states you need to distinguish between. If you had any more states, it would be too many. If you had any fewer states, it would be too few to actually understand the process. So you have like stochastic processes, there's hidden Markov models, there's epsilon machines. Then I think there's something about like these inference hidden Markov models where if like I'm seeing the outputs of a stochastic process, if I'm seeing just a sequence of heads and tails or tokens or whatever, there's some process where I'm coming to have probability distributions over like what the what state the thing might be in. I update those distributions, and that itself works kind of like a hidden Markov model, where the states are my states of knowledge, and the transitions, the tokens and transitions are like, I see a thing, I move from this state of knowledge to this state of knowledge. So I also see this construction of going from underlying processes of generating to like the process of inferring things. And I guess there are some interesting differences or similarities and differences between like the inference process and the generation process. My impression of computational mechanics is it's taking that whole thing, these stochastic processes, these like hidden Markov models, these epsilon machines, these inference hidden Markov models. You probably call it something like, you probably have a better name for them than that, but that's like what I came up with.
Maybe mixed state presentation.
Mixed state presentation, yeah. And then there's this question of like, okay, how do I like calculate interesting things about these processes? How do I like actually, find stationary distributions, or how do I like get observables or higher order statistics out of that? This is what I've gathered from computational mechanics. I'm wondering, does that seem right? Am I missing stuff?
That was pretty good. I think there's a lot there. I'll just kind of go at it without any particular order. But so importantly, you brought up the epsilon machine. So for instance, one extra thing we can add on to what you said is that there's kind of a distinction between minimal for the purposes of predicting versus minimal for the purposes of generating. Okay. And so the epsilon machine is the minimal machine for the purposes of prediction.
Okay.
In general, you can get smaller machines.
Where a machine is like a hidden Markov model?
Yeah, I think it can be a little bit more general than that. But yeah, I think it's fine to think of it as an HMM. So yeah, the mixed state presentations are HMMs in this framework, and the epsilon machine is one. And you notice they actually both generate the same data set. So you can think of kind of you have data, right? So like the data, for instance, that you train a transformer on, all of your training data.
Yep.
And these can even be, in theory, not for a transformer in practice, but in theory, these can even be kind of infinite strings.
Yep.
If you want to make an HMM that generates that data, there's kind of an arbitrary choice a lot of the times. There are many, many HMMs that can generate that data, an infinite number of them, in fact. And in CompMech, they call these different presentations. And Paul, in one of his papers in the intro, makes kind of a really great point, and kind of this is like a deep conceptual view that I really love about CompMech, which is that kind of for different questions about a process and for like the structure of the data, different presentations allow you to answer those questions kind of with different amounts of ease. So if you want to ask questions about kind of the predictive structure and what information you need to predict, then an epsilon machine or a mixed state presentation is like a very good way to answer that question. Do you have some question that's different about generation or about pairwise correlations? Then different presentations will be more useful for that. So just this notion that the way that you present the data, kind of the choice that you have of exactly which machine you use to generate the data with, even though it's the same exact data with the same structure in some sense, kind of allows you to answer different questions. So that's just a few thoughts. I
guess you had a lot to unpack there in what you said.
Right.
So there are a few things I wanted to at least comment on. The first one is, I think, a common misconception. I think it's natural that you were saying, it seems that computational mechanics is about HMMs. And I guess that's a kind of common misconception. I'd say that actually HMMs turn out to be the answer to a particular question you can ask in computational mechanics. So like the data generating structure could be essentially anything. You could think through the Chomsky hierarchy or other types of, ordinary differential equations or whatever that generates the thing.
Okay.
And then you ask the question of, again, what is it about the past that I need to remember to predict the future as well as possible? And then you have these minimal sufficient statistics, which are these kind of coarse grainings of the past. And then you look at what's the metadynamic among those kind of belief states about the world, like you mentioned.
Okay.
And then that thing turns out to be describable always as a hidden Markov model if we allow ourselves infinitely many states. Because you can think about this basically via Bayesian updating, that given basically your knowledge of the world up to some point. Like even if you know the data generating process, you don't know the hidden state of the world, right?
Yeah.
You just wake up in the morning and you have this impoverished view. You need to take in data and synchronize to the state of the world. So you know something. You have something like a model of the world. Your data so far induces some belief state. And then as you take in more information, how do you update your belief? Of course, just Bayesian updating. And so from a particular belief state, there is a unique answer of where you go to given the new data. So that induces a hidden Markov model.
Right.
In fact, it induces a particular type of hidden Markov model, which kind of in the lingo of computational mechanics is unifilar. But you can also think in like the theory of automata, this is called deterministic. That's a little confusing because we're talking about stochastic deterministic automata. So unifilar is kind of a better name. Like you're following a single thread through the states of this belief structure.
Right.
So
just to clarify, it's like stochastic in the sense that the states of knowledge are, probabilities over what's going to happen in the future, but it's deterministic in that if you see a thing, there's just a deterministic next state of knowledge you go to.
There's a deterministic way to update your state of knowledge, right?
Right.
Yeah. And there's typically some stochasticity in terms of what in the world comes at you.
Yeah.
Right?
Yes.
And so if you look at like an ensemble of realizations, there would be kind of randomness stochasticity in terms of like the transition rates between belief states. But in any realization, there's like a thing you do to make your beliefs. And then just a few other things I wanted to engage with were what's the role of the epsilon machine here?
Yep.
So I think especially for making a connection with understanding neural networks, I think the epsilon machine isn't as important. I think this mixed state presentation, this updating beliefs is the primal thing that we care about.
Okay.
And it doesn't even require stationarity or anything like that. If you do have stationarity, then there will end up being some recurrent structure in the belief state update. And then those recurrent belief states are the causal states of this epsilon machine. So I think it's a bit of like the history of where CompMech came from, that the epsilon machine was important. And I think for the current way in which CompMech is useful, I think the epsilon machine is not as important. But it is still interesting to say what are the recurrent states of knowledge that I would come back to for something stationary, which maybe is relevant if you're like reading a long book or something. But
okay.
Yeah.
So can I try my new understanding?
Okay.
And see if I've gotten any like novel misconceptions. Here's my new understanding. You've got the stochastic processes. Stochastic processes are just like things that generate sequence data, like the probability distribution over books that are going to be written, and a book is a really long sequence of words in this frame, or sequences of the state of some chaotic process, maybe just like sequences of stuff. You want to like understand this probability distribution over these sequences, like what's going to happen in the future given the past. And it turns out that hidden Markov models are kind of a universal way of describing these stochastic processes. Like if you have a stochastic process, you can create a HMM, hidden Markov model, that generates it. And in fact, you can create a bunch of hidden Markov models that generate it. There's also this process of updating your beliefs, given like some data that you've seen in this process. And that also looks kind of like a hidden Markov model. Maybe not exactly, because things are coming in instead of going out, but something like that. And computational mechanics, as I currently understand it, is something like, okay, how do we relate these stochastic processes to hidden Markov models? Like which hidden Markov, you can construct a bunch of hidden Markov models that correspond to the same stochastic process. Which one do we want to like play with? And, which one is most useful for various mathematical goals we might have for understanding this sequence? If we want to understand the inference process, like, we can think of that in terms of some kind of hidden Markov model-like thing. And then there's just this process of understanding, like, okay, what actually happens? How, maybe you haven't said this, but I imagine there might be questions like, okay, how many states are there? What are the dynamics of belief updating? Where do you go to? That's what I now hypothesize computational mechanics is. How does that sound? What am I missing now?
I'd say you've hit on a lot of relevant things. I think maybe even more interesting topics would come up if we're thinking about, what does any of this have to do with neural networks? Because like I said, computational mechanics is a very rich field. There's like, semester-long courses on this. So I don't think we could do it justice like right away. But I think we can get to a lot of neat ways in which the theory is being used and extended by us and our colleagues, as we're saying, okay, how can we utilize this to, well, what have we done so far is basically we have this new angle at understanding internal representations of neural networks, and also something which I think will become more clear in our upcoming work, the behaviors of models, like what to anticipate in terms of model behavior in context learning. And there's like really an amazing number of ways now to adapt the theory that we see, which is getting us to answer questions that I'd say wasn't obvious to even ask before.
Cool.
I had a thought just because of something you said. One of the things we've been talking about recently is this. We've been thinking about a lot of the work that's been going on in interpretability that uses the concept of world models and kind of what the form of that work is, and trying to get closer and closer to like, what is a world model? What is the type of stuff people do when they talk about world models in interpretability work? And this comes back to this issue of where HMMs fit in comp mech, and are we kind of assuming an HMM or something? I think one of the things I've been thinking about, even if you don't have stochastic data, right? If you have some other data structure, and there's like a lot of data structures that one could have, right? You have some implicit or maybe explicit structure to the world in which you want to ask, does this transformer represent somehow in its internals? Well, no matter what that data structure is, at the end of the day, if you're going to train the transformer on it, you have to turn it into sequential data, right? It takes sequences of tokens. And so, you can go in and you can kind of probe the model internals for structures associated with this original data structure in your head that might not have anything to do with sequences, right? That's a fair game to play. And I think people sometimes do that. Like maybe you conceptualize Othello as not really being about sequences, but being about some other type of data structure, about kind of like states of the board where, the top left corner is black, white, or empty.
Right.
And then you can go in and you can probe your Othello GPT to see if that's linearly represented in the residual stream. But when you train the Othello GPT, you are transforming the game of Othello to a specific tokenization scheme that gives you specific sequences. And those sequences, are kind of naturally thought of as an HMM. And then we should be able to, if this work isn't done, so this is more kind of thoughts and things we hope to do, but we should be able to take results like that, kind of reframe it from a comp mech point of view, and then run our analysis and kind of apply our framework to it to kind of even make, hopefully, theoretical claims explaining the results that they've gotten, right? That certain probes for kind of properties of the game state are linearly represented and others are non-linearly represented. If we take our findings seriously, that kind of this belief state geometry, I guess we haven't spoken too much about that yet. But if that belief state geometry is kind of the thing that the transformer is trying to represent, then hopefully we can kind of explain a bunch of these other results that people have been finding.
I think first I just want to make sure that I really understand what this theory is before I move on there. But I'm chomping at the bit to get to that later. Okay, here's a really basic question. Why is it called computational mechanics? Like, does it have something to say about computation or mechanics?
Yeah, it's a kind of interesting historical note. I think it makes more sense when you realize it's called computational mechanics in distinction to statistical mechanics, which, okay, this makes some sense. What's statistical mechanics in physics? There is this theory of thermodynamics, of course, which is this high level. You just look at these macro states and how they evolve. Thermodynamics doesn't require a microscopic description, but then it turned out that, actually, if you believe in atoms, which, I mean, this is kind of why people started re-believing in atoms, then you can actually explain some of the thermodynamic behaviors, and you can figure out material properties and stuff. How? Just by saying, like, basically by saying how random something is. So we have entropy, right, that quantifies that. And by saying how random something is, we can derive all of these properties. But it's kind of a static view of what's going on. You just look at the statistics.
Yep.
Okay. When the question shifted to say, what are the dynamic aspects? What are the computational aspects? Somehow there's like nature's intrinsically computing. You can think of Shannon's channel of that information would go through. You can also think of the present as a channel that the past must go through to get to the future, right? So if you take this on, there's some sense in which nature's naturally computing the future from the past.
Okay.
So that's kind of the idea of computational mechanics. And yeah, it's also, it's taken and built upon a lot of ideas in computer science and information theory. Unfortunately, it also has the same name as something which is quite different, which is like, I don't even know exactly what it is, but it's like,
how to use computers to model like Newtonian mechanics.
Something systems. Like that, yeah. So it's like, so that's a bit confusing. But yeah, the computational mechanics that we're talking about here is in distinction to statistical mechanics.
Got it. I guess the final thing that I want to ask is, a thing you mentioned a bit offhandedly was this idea of how can you do prediction under some sort of like resource constraints of like not being able to, maybe it was not being able to distinguish certain states of the world, or maybe it was something else. Like, I'm really interested in that because I think this is a question that like Bayesian statistics doesn't have an amazing answer for just off the shelf. It's a question that is obviously really relevant to AI.
Yeah.
Can you tell us a little bit?
Yeah, we're also really interested in this. I mentioned that some work has been done in CompMech on this, but I'd say it's kind of underdeveloped. But like Sarah Marzin and other colleagues have worked on thinking of rate distortion theory. How does it apply in this dynamic framework of computational mechanics when maybe your memory is limited?
What is rate distortion theory?
Conceptually, you can kind of imagine a plot where on the x-axis you have kind of your memory capacity, and on the y-axis you have your accuracy at predicting the future, and there's some kind of Pareto optimal curve you can get. So for a certain amount of memory constraint, you can only get so far in accuracy, and there's some curve that describes the optimal trade-off there.
So shape of the curve, I guess probably how you get to the curve. And so you were saying there was some work by Sarah Marzin and others on taking some sort of rate distortion theory view and applying it to, I think, dynamical processes or something?
Yeah. So say instead of the causal states, instead of these ideal belief states, how would you compress those to still predict as well as possible given the memory constraints? So there's this is related to like information bottleneck methods. There's this causal bottleneck stuff. So that's one way in which you can think of a constraint. There's memory constraints, but there can be all sorts. There's an interesting avenue on the physics side where actually if you allow yourself something like quantum states, quantum information can somehow compress the past better than classical information could. So there's this interesting branch of computational mechanics which has said actually we can use quantum states to produce classical stochastic processes with less memory than otherwise classically necessary. So that's interesting. Sounds very tangential, but a bit of a teaser. Actually, we think that neural nets do this. So that's a bit wild. And again, something you just probably wouldn't think to look for if you weren't building off this theory.
Sure. I guess to finally to just triangulate computational mechanics a little bit more, I want to compare it to two other things that sound kind of similar. So the first is people who have followed the AI safety space, people who have listened to a few episodes back in my podcast might be familiar with singular learning theory, right? So this is the this is the most recent, really mathy way of thinking about Bayesian statistics that has taken the alignment world by storm. How do you see computational mechanics as kind of contrasting with singular learning theory, perhaps both in just what the theory even is or is trying to do and how it might apply to AI systems?
I have a quick comment, maybe then Adam wants to elaborate, but at a very high level, computational mechanics is kind of a model agnostic theory of prediction.
Yeah.
Whereas I think SLT takes on very seriously that if you have a particular model in that you have a particular parameterization of the model,
Yeah.
then what's learning like? Singular learning theory, SLT, is a Bayesian theory. So I think sometimes the way in which it's applied to talk about actual learning with maybe stochastic gradient descent confuses me a little bit. But I think it's a genuine mathematical theory that I think likely will say something useful about inference. Maybe it can be complementary to CompMech in addressing some of those aspects. Do you have further thoughts on that?
Yeah, I guess, I mean, first of all, I'm not an expert at all on SLT, although I've been like highly inspired by them and like the entire group at Timaeus.
Mm-hmm.
I think they ask a lot of very questions that are similarly motivated. So for instance, I think they really do a good job at kind of talking about their motivations about kind of the computational structure of these systems and how can we get a mathematical and theoretical handle on those things. I think their kind of tactic and framing of it, and this might be more of a vibes thing than like, again, I'm not an expert in the math at all, so I really can't speak to that. But I think kind of naturally they take a view that has more to do with learning and the learning process. And
Right.
I think they want to, at the end, say something about kind of the structure of that learning process and the geometry of the local landscape and how that relates to the computational structure at a particular weight setting. Whereas I think CompMech kind of most naturally, at least, takes a view that really has to do with the structure of that inference process kind of directly. But then,
Right.
of course, one can think of extensions. Paul's already done some work kind of extending that to the learning process a little bit. So yeah, in some sense, it's kind of, I think they're trying to get to a very similar set of questions. And a lot of these are like, I consider deep conceptual questions at the heart of like, how do AI systems work? What does it mean to talk about structure of computation? What does it mean to talk about the structure of training data? But from kind of different starting points, the
Right.
learning process versus the inference process.
Right. Yeah, in some ways they seem sort of dual, right? Like,
Yeah.
figuring out the weight updating process versus fixed weights. Like, where should it go? The other thing I want to ask to triangulate, again, a somewhat recent episode of Excerpt, is when I hear people talk about, oh yeah, we've got a really nice mathematical Bayesian theory of, updating based on evidence, and we're going to use it to understand intelligence. One place my mind goes to is like active inference, this Carl Friston style work. I'm wondering if there's like any interesting connections or contrasts to be brought out there.
I think, again, this will kind of also be a little vibesy.
Sure.
And I think the active part of active inference is talking about, as far as I understand it, an agent taking actions in the world.
Yep.
There's kind of a part of CompMech that has to do with interacting systems called transducers. And that is so far not what we've applied to neural networks. So that part's a little different if you just take kind of the not transducer part of CompMech, at least, and compare it to it. Yeah. Also, I guess like the way that I view active inference, again, as a non-expert, is it takes seriously, I guess it matters what form of active inference. So often it starts with just kind of like, we think the brain's doing Bayes or like an agent is some Bayesian thing, and then you can get it down to an actual formula by kind of assuming, it's hard to do Bayes in full. So like, let's find some kind of mathematical way that you can approximate it. And they kind of get to a specific set of equations for that Bayesian updating. And so it kind of assumes a certain method of approximating Bayesian inference, where again, like, I don't know, we're pretty agnostic to all that stuff in CompMech. So yeah, those are just some thoughts.
Sure. I guess I am limited in my ability to wait until I dive into your paper and your interesting work. But is there anything you would like to say just about computational mechanics as a theory before I dive into that?
I guess just to reemphasize that two things. One, it's as it is currently not the answer to everything, but has been really useful. But also, I think it's a great springboard to continue on. So we've recently founded this research organization, Simplex, because we believe that we can really build on this work in useful ways. So, I mean, I just kind of that contextualization.
Sure.
Help.
Yeah, let's talk about building on it. So you've recently published this paper, Transformers Represent Belief State Geometry in Their Residual Stream, by Adam, Sarah Marzan, Lucas Teixeira, Alex Skeeteling-Oldenseal, and Paul. What do you do in this paper?
Yeah, so we kind of were motivated by this idea of like, what is a world model? What is kind of fundamentally the structure that we're trying to get these, that we're training into these transformers when we train them on next token prediction? What is the relationship to that structure to a world model? How can we kind of get a handle on these questions? I guess one of my own personal, I don't know if it's a pet peeve, but something like a pet peeve is just these, like, it feels like often there's just this kind of never ending discussion that happens in kind of the AI community at large about, are these things, do they really understand the world? Do they have a world model? Do they not? And these things, these are slippery concepts. And it feels like the same conversation has been happening for a while now. And our hope is that if we can kind of get to some more concrete handle, then we can actually know what everyone's talking about. We don't have to keep on talking past each other. We can answer some of these questions. So the tactic that we take in this paper is to kind of start with a ground truth data generating process. So we know kind of the hidden structure of the world, so to speak, that generates the data that we train a transformer on. And then we can go in and we can first make predictions using the theory of computational mechanics about what structure should be inside of the transformer. Then we can go and we can see if it is there. The structure, so we need a way to like figure out what we should look for in the transformer. And so we need a way to go from this hidden data generating structure, which takes the form of an HMM in our work, to a prediction about the activations in the transformer. And this, so we just ask the question, what would it mean to, like, what is the computational structure that one needs in order to predict well, given histories, finite histories from this data generating process, if we want to predict the next token? That in computational mechanics takes the form of something called a mixed state presentation, which describes how your belief about which state the data generating process is in, how that belief gets updated as you see more and more data.
Right.
And that by itself doesn't give you a prediction for what should be inside the transformer, because that's just kind of another hidden Markov model. But there's a geometry associated with that. And that geometry is given by virtue of the fact that your beliefs over the states of the generative process are themselves probability distributions. Probability distributions are just a bunch of numbers that sum to one.
Right.
And you can plot them in a space where kind of each thing they have a probability for. In this case, it's the different states of the generative process or a different axis. And And so the points lie in some geometry in that space. And in the main example, or one of the first examples we used in the paper, and it's featured in that blog post on Less Wrong, you end up getting, even though it's a very simple generative structure, you end up getting this kind of very cool looking fractal. So it feels like a highly non-trivial geometry to kind of expect and predict should be in the transformer. And what we find is that when we try to find like a linear plane inside of the residual stream, that when you project all the activations to it, you get the fractal, you can find it. And not only can you find it, you can perform that analysis over training, and you can kind of see how it develops and refines to this fractal structure. So we were...
And that it's linearly represented.
Yeah, and
also,
it's linear.
which is
Yeah.
a big deal.
So yeah, we were very excited about that. It means that we have some kind of theoretical handle about, like, given the structure of our training data, what we should expect geometrically in the activations of a transformer trained on that data. So it gives us a handle on kind of model internals and how it relates to training data.
Gotcha. Yeah, I think, like, when I'm thinking about this, one thing I'm paying attention to is, like you were said, what does it mean for a thing to have a world model? And I see, like, I guess the part of the contribution of computational mechanics is just distinguishing between kind of the dynamics of generating some sequence and the dynamics of, you know, what inference looks like what states you go through with inference. And would it be right to say that, like, a big deal about your paper is just saying, like, hey, here's the dynamics of the inference that we think, like, Bayesian agents should go through when they're, like, inferring what comes next, or sorry, even just inferring, like, the whole future, and saying, like, hey, we found the dynamics of inference encoded in this HMM. Or sorry, encoded in the neural network. Sorry.
Yeah. I guess one of the points that we kind of hope is obvious in hindsight, but I think a lot of good results are obvious in hindsight, so it's hard to feel proud of yourself. But it's just this thing of, what does it mean to have a world model? And we just took this question pretty seriously. What's the mathematics of it? And then there's these speculations. Can next token prediction do this? And then the answer is concretely yes. In fact, not only must neural nets learn a generative model for the world, but they also must be learning a way to do Bayesian updating over those hidden states of the world. And I guess then what's more, it's not just tracking next token probability distributions. The model will differentiate basically states of knowledge that could have identical probability distributions over the next token, which seems a little odd if you just think about, I'm just trying to do well at next token prediction. But again, in hindsight, kind of makes sense that if there will be a difference down the road and you just kind of merged those states early on, then even if your loss at this time step or at this context position is just as good, eventually as you move through context, you'll have lost the information needed to distinguish what's coming at you. So that's kind of this thing about predicting the whole future is because, well, it's just this iterative thing. If you do next token prediction on and on and on, eventually you want to get the whole future right. And not only is there this causal architecture, but as Adam said, there's this implied geometry, which is pretty neat. And I think there's all sorts of hopes, and we've had a lot of good community engagement. People have talked about, well, maybe this means we can back out what a model has learned if we can somehow automate the process of this, simplex discovery. There's a lot of, I think, directions to go that we're excited about, and we think the community can also help out.
Just to add one thing, to reiterate the point that you made about the structure of inference versus the structure of generation. I do think this is, at least for me, it was like a super core conceptual lesson coming from a neuroscience background, because in kind of the section of neuroscience I was in, at least, we would talk a lot about kind of, the cortex's role is to do this, to implement this predictive model. But then we would always kind of instantiate that in our minds as generative models. It's like, if you asked any particular neuroscience in that field, including me just a few years ago, like, yeah, but don't you have to use the generative model to do prediction? You'd been like, yeah, of course you have to do inference over it, but it'd be kind of like a side thing. Like once you have the generative model, it's like obvious how to do inference, and there's like not much to it. That would be kind of the implication. But actually the structure of inference is enormous, right? From this 3-state HMM, and this is a simple example, we get an infinite state inference structure that has this fractal thing. So like the structure of inference itself is not, something to just shrug away. In some sense, it's like if you're trying to do prediction, it is the thing. And its structure can be quite complicated and interesting. And so like I actually think the neuroscientists could actually learn kind of a lot from this too. Although obviously we applied it to neural networks. Yeah.
Sure.
And I guess there's maybe one other idea that you could usefully latch onto here, which is something like thinking of predator and prey. It's like you can have like a fox and mouse or something like that, and the mouse can be maybe hard to predict or eat with like a simple generative structure. It just does something.
Yep.
And all the fox has to do is predict what it's doing. But it's not sufficient for a fox to be able to act like a mouse. It has to actually predict it. And that's maybe some evolutionary pressure for it to have a bigger brain and things like this. And I think this is like, okay, is this a weird analogy? But I think it's actually quite relevant. Like how smart should we expect AI models to be? It's not just that they need to be able to act like a human, like they need to be able to predict humans. And that's a vastly greater capability. We can't do that with each other too well. I mean, we do a little bit,
but it's hard.
But it's a superhuman task, actually. Yeah.
Yeah. Have you played the token prediction game?
Oh, no.
I've played various versions of this. I don't know if it's the one you're referring to.
Yeah, it's just a web app that like it's basically the game is to literally do what these transformers have to do. So you see just a prefix, or actually I think you start with 0 prefix. You just have to guess what the next token is. I think it even shows you like 4 possibilities or something. And you have to just guess, what is the next thing going to be? And then it gives it to you. And then you have to guess, okay, what is the next thing going to be? And it's really hard. Yeah, I don't know. Somehow I had never like made this comparison before, but it's much harder than writing something.
Yeah, for sure. And there's also something interesting in that, I'd say, meta dynamic of doing the prediction, which is as you get more context, you'll probably be better at predicting what's next. Okay, now I have some context, right? And so this is some quantitative sort of stuff that just once we take these ideas seriously, we can say, oh yeah, as you move through context, your entropy over the next token, if you're guessing, should decrease. How does it decrease? Actually, that's like one of the things I worked on during my PhD in Computational is like, oh, there's this way to calculate this via like the spectral structure of this belief state metadynamic and all that. But like there's something to this of that models, since they're predicting, they should and they will converge to users in context. What is that? That is a definite type of in-context learning. It's a bit, I think, our task to show whether or not that's the same of what other people call in-context learning. But that's a very concrete prediction that, especially with non-ergodic data, which is the case for us, that in general you're going to have this power law decay of next token entropy, which is borne out empirically.
Sure. Okay. So there's a ton to talk about here.
Yeah.
First, I want to ask kind of a basic question. Just aesthetically, if I weren't like trying to read your paper, one of the coolest things about it would be this like nice colorful fractal that you guys have, right? Why is it a fractal?
So I guess one way to think about that is, what is a fractal in general? Well, fractal is something like iterating a simple rule over and over, right? That's a self-similar structure you get out of that. Well, what's the similar rule? Well, we have a simple generative structure, and then you're doing Bayesian updating over that. There's like different types of outputs that it could give. Each output gives a different way of doing Bayes updates over whatever your distribution of the states is. So you're doing the same thing over and over, and the geometric implication of that is fractal.
Okay.
Is that helpful?
I think this maps onto what my guess was.
Yeah, I'll also point out that kind of after the Less Wrong post we made, John Wentworth and David Udell made a follow-up post.
Udell or Laurel?
Laurel.
Okay.
Sorry. Made a follow-up post kind of explaining that iterative game structure. And then there's also been kind of academic work kind of explaining the same thing from the point of view of iterative functions from Alexandra Jurgens. So those are two kind of resources.
Mm-hmm.
Cool. The next thing I want to ask is picking off a thing you mentioned very briefly of like potential follow-up work being like, try and find this fractal structure as a way of understanding what the network has learned. Is there something to say about like, so you have these fractals of, belief states from this mixed state presentation or something. Is there some way of going from here's the fractal I found to here are the belief dynamics?
Yeah, I think this is getting at an important point that the fractal is those are the beliefs. They're not the dynamic among the beliefs.
Yep, they're not the updates.
Yeah. And I think there's kind of an obvious thing that we'd like to do is like, can we, now that we find this thing, is it now natural to do some like mech-interp sort of thing of finding a Bayesian updating circuit? Well, that would be nice. It's not totally clear how this works out, but it's a natural sort of thing for getting at hopefully a thought process of the machine, right? I mean, like what is its internal dynamics among these beliefs is a great question that we are pursuing. A lot of this is empirical because, now we have this theoretically grounded thing, but we also need to work with the actual implementation of like transformer architecture. How does that actually instantiate the thing?
Yeah. I guess I also just have a theoretical question of like, okay, suppose you had this fractal somehow. You had it to infinite precision. Is it possible to back out the belief HMM or the stochastic process? Or are there like multiple things that go to the same fractal?
So there would be like multiple choices. Like there's degenerate ways in which you can choose to represent a generative structure.
Right.
But it's all the same stochastic process. So, and that's the thing that matters.
Right.
The world model that it has. So there really shouldn't be that much degeneracy at all. In fact, in the current kind of toy models that we've used to say what happens in kind of the simplest framework, then we have to project down. We have to find a projection in the residual stream where this fractal exists.
Yep.
Actually, probably in frontier models, the residual stream is a bottleneck. So you're not going to have to project down. It's going to try to use all of its residual stream. So in fact, it maybe is easier in a sense, but then it's also doing this probably lossy representation that we're also trying to get a handle on.
Yeah. I guess I wonder, so if it is kind of, if one fractal does correspond to one generative process, maybe we don't even need to do mechanistic interpretability. And we can just say like, oh yeah, here's the geometric structure of, the activations. Bam, this is the thing that it learned.
Yeah, I think I don't want to overstate what we're claiming here. I think the way that I would think about what this belief state geometry is not kind of, maybe it'll be useful to try to think about like features, the way people talk about and what they are and what the relationship is between features and these belief states, even just kind of philosophically. I think it would be a mistake to claim that the belief states are the features. I think of features at the moment, at least, and they're kind of ill-defined, but I think of them as the kind of computational atoms that the neural network will be using in the service of building up the belief state geometry and the dynamics between those belief states. Now, I should say that I think, and of course, how a neural network builds the belief state geometry up will be highly dependent on the exact mathematical form of the network they're using. So in transformers, the fact that you have a residual stream with an attention mechanism, the attention mechanism is literally the only place the transformer can bring information from the past to the current token position. And so and it has a certain mathematical form. It's like, strangely, a lot of it is linear, not totally, obviously, but that mathematical form kind of puts constraints over what information can be processed from the past to the present, and it puts strong constraints over kind of exactly the manner in which you can kind of build up this belief state dynamic. So yeah, it would be really cool to be able to even kind of, it's like a version of CompMech that somehow takes into account the kind of mathematical constraint that the attention head puts on you in your ability to bring information from the past to the present, which we very much don't have, but which you could vaguely imagine.
Although Adam has done some preliminary experiments where you look at basically how, like this fractal we were talking about, how that's built up through the layers and in the different, like from attention, from MLPs. And I mean, it's surprisingly intuitive and beautiful. So encouraging, at least.
Yeah. So for instance, if you take the fractal example, in the MES3 process, it's a vocab size of 3. So it only speaks in kind of A's, B's, and C's. So it's just strings of A, B's, and C's. And then you put it through the embedding and you see just kind of 3 points. So it's like 3 points in a triangle, one for each of the tokens. That makes sense. And then that's the first place that you're in the residual stream. Then you kind of split off and you go into the first attention mechanism. And what you see happen in the first attention mechanism is it kind of spreads out the points to like a filled in triangle.
Okay.
And then when you add in that triangle back into the residual stream, you're adding in the triangle to these 3 points in a triangle. And what you get is 3 triangles in the shape of a triangle, and then so on and so forth. And you can kind of see, and then actually it goes into the MLP, and you can see it kind of stretch out these 3 stacked triangles to look more like the simplex geometry. And then every time you go through another layer, it adds kind of like more holes and more triangular structure. And you very nicely see kind of a very intuitive feeling for how every part of the transformer mechanistically puts in extra structure in order to get to the belief state geometry.
And I think this is one example of how we hope that computational mechanics can be something like a language for bridging between mechanism and behavior. That a lot of mech interp has been great, but it's pretty low level. There's just results here and there. So one thing computational mechanics can do is create a language to tie this together, to unify the efforts, but also like, where's this leading? And so hopefully there's a little bit more of a bridge between the mechanism and behavior.
Sure. So there's this question about like what we learned, and we've talked about that a little bit. One thing that, so yeah, we've learned that like these fractals, they're represented. You can like get this mixed rate presentation in the residual stream. Another result that comes up in the paper. Well, one result is that it's linear. Even in retrospect, like, are you surprised by that? Or do you think you have a good story for why it should be linear?
I don't have a good story. And in fact, computational mechanics doesn't, as far as I know, it does not give it right. It just says that the mixed state presentation should be there.
Yeah.
Mm-hmm.
It doesn't say how or where.
I think when we decided to do these experiments, we're like, based on this theoretically informed thing, like, yeah, somehow this geometry should be in there. These belief states should be in there. Even this geometry should be in there. But at least it's going to be stretched out or something, right? But it's like, okay, there's still definitely something to explain. And I think I've seen titles and abstracts of papers that I feel like maybe help us to understand why things are linearly represented, but I don't yet understand that well enough.
Gotcha.
It's like too good to be true, but hey, good for us.
Yeah. Maybe this just has a similar answer, but another result that comes out is that at least in one of these processes that you train a transformer on, there's not like one layer in the residual stream that you can probe and get this nice simplex. You have to sort of train a probe on all of the layers, right?
Yeah.
Is there a story there of just like, well, one layer would have been too good to be true, or is there something deeper?
Actually, in that case, there is kind of a deep reason that computational mechanics gives for that finding. Although I should say we were not looking for that finding. That's just kind of, I think one of the nice things about having kind of a theoretical foundation for the way that you go about running your experiments is that sometimes phenomenon jump out at you, and then in hindsight you realize that the theory kind of explains it. So in this particular process, this is the random XOR process, where if you start from a particular state, you generate a bit, a 0, 1, then you generate another bit, 0 or 1, and then you take the XOR of the previous two, and then you generate a bit XOR, so on and so forth. So that's your data generating process. It has 5 states in its kind of minimal generative machine. And that means that the belief state geometry lives in a 4D space. And actually, unlike kind of the fractal thing, you actually get 36 distinct states. It's also quite a beautiful structure. Maybe there's a way to splash that on the screen. And
probably we have a low budget. I'm sorry.
Yeah, okay. Okay, but it kind of looks like an X-ray crystallography pattern. And so it's aesthetically pleasing. But importantly, multiple of those belief states, even though they are distinct belief states, they give literally the same next token prediction.
Yep.
So what does that mean? The transformer, all it needs to do kind of at the, like if we just think of the last layer of the transformer and how it actually gets made into a prediction for the next token, you just kind of read off of the residual stream with the unembedding and convert it to a probability distribution. But that means that at the end, at the last layer, you actually don't need to represent distinctions in next token predictions.
Right.
And in fact, not only relative to the kind of local thing of doing the next token predictions, but there's no attention mechanism after that. So even if you wanted to represent it there, it could never be used there because it could never interact kind of and send information into the future.
Right. Not of the next token, but of everything else.
Yeah. So in fact, but still COMEX says the structure, these distinctions should be there. They don't need to be in the last layer, but they do need to be somewhere. And so, yeah, well, you see them in kind of earlier layers. So that's an explanation for why it's not in the last layer.
Yep.
Yeah. And I think this kind of hints at maybe how the transformer is using the kind of past construction of the belief states, that if it's earlier on, then you can leverage those across context a little better. So I think there's like strong interplay here between theory and experiment, that there's still a lot for us to figure out.
Sure. Mm-hmm. Is there, sorry, just a very basic conjecture I have after hearing you say that is just that, like, you know, the parts that are relevant for next token prediction are in the final layer. The parts that are relevant for token after that prediction are in the second to last layer.
Well, I don't think it's quite that clean. Okay. Because if that's the case, then you'd only be able to model like Markov order n processes where n is the number of layers.
Yep.
So it's not going to be quite that clean. But it's something like at the end, you really only need the last token distribution. Okay. But then also the theory says that somewhere in the model, somewhere in the residual stream, there should be these representations of the full distribution over the future. And it does seem that to be able to, for a certain context position to look back and utilize that, it would serve a purpose for those to come about early on. It's still not clear to me why bother shedding them. Like, they could persist as far as I'm aware, but there's not like a pressure for them to persist.
Sure.
So I'd like to understand that better.
I'm sorry to get hung up on fractals, but I have another fractal question. So this random XOR belief state thing didn't form a fractal. Is that just because the fact that like 1 in 3 bits is deterministic, does that just sort of snap you to like one of these like relatively well-defined states? Is that what's going on?
I wouldn't classify it that way. But the distinction, I think one way to anticipate whether or not you're going to have a fractal structure is whether the minimal generative mechanism is this thing I alluded to earlier about whether it's unifilar or not.
Okay.
whether it has these deterministic transitions between hidden states.
Right.
Okay. So the random XOR, the minimal generative mechanism, is a 5-state thing, and it's also a 5-state unifilar thing. So it kind of is the recurrent belief states. So you have these 36 belief states in general that then will eventually, as you go through resolving these different types of uncertainty, you'll eventually get to these 5 states. So okay, that's kind of simple. Whereas if you have even a simple generative mechanism, let's say you can have as small as a 2-state hidden Markov model that generates the thing, but it's non-unifilar in the sense that if you know the current state of the machine and you know the next token, it still doesn't tell you exactly where you end up. So the number of probability distributions induced can be infinite, and generically is. And so in that setting, again, you're folding your beliefs over and over through Bayesian updating.
Right.
So in general, if you have a minimal generative model, which is non-unifilar, Bayesian folding will give you a fractal. And if the minimal generative structure is unifilar, then you won't. So that's also kind of nice that we can expect that.
Sure. Cool. Again, speaking of fractals, so in the paper, you basically say, hey, here's like the fractal we expect to see. Here's the fractal we get. And it's like pretty close in, mean squared error. It's like way closer than if you like had a randomly initialized network, or way closer than it was during the start of training. And my understanding is you're measuring this in mean squared error terms, right? Another way or a similar question I could ask is, okay, suppose that instead of like the mixed state presentation of the ideal process, I just had this thing I got from the network. How good a job would I do at prediction? I'm wondering, is that like a question that there's a nice answer to? And do you know what the answer is? And if you do know what the answer is, please tell me.
So it's a little unclear to me what you're asking, but if you might be asking something like, can we do something with the activations if we don't know the ground truth of the generative structure? Is that right?
Or like, instead of measuring the distance between activations and ground truth by a like mean squared error of this probe, one thing you could do is say, okay, like imagine this is the mixed state presentation I have. How good a job am I going to do at predicting the underlying, like the actual thing? Like somehow like the thing you've probed for seems like a lossy version of the underlying fractal. How much does that loss show up in prediction as opposed to reconstruction error?
The one thing you should be able to do is, and this is maybe not this is not like an infinitely general answer to your question, but if you think of kind of the fractal that is the ground truth mixed state presentation, and then you think of coarse graining that fractal to a certain amount. Sarah Marzin has work kind of going through the math of the implication for that for predictive accuracy. And that kind of intuitively, I think, makes sense. And in general, I think it should be possible to work out kind of given any particular coarse graining. So what does that mean in this particular case? It means like if you take just kind of some volume in the simplex, and you just kind of say, I know I'm in this area, but I don't know where exactly. I don't know exactly which belief state I'm in, but I know I'm like somewhere there. You should also be able to calculate the consequences of kind of that and its implications for next token predictive accuracy or cross entropy loss. And what that looks like in terms of kind of the visual of the fractal is exactly the fractal just getting fuzzier.
Yeah. Nearby points in the simplex do make similar predictions. So
Sure.
There's some sense in which like, if it looks fuzzy, then you can almost visually like say how that's going to turn out for prediction, and we can quantify that.
Right. And am I right that this is kind of because the simplex is like its distributions over hidden states, and therefore like being close by in the simplex is just close by in like your whole feature predictions rather than just
Yeah.
next token predictions.
Yeah,
Right.
you can think of how do you calculate probability of future tokens from a distribution over the model.
Yeah.
And it's basically linearly in terms of the distribution over the model. And so if you slightly reweight, there's like a continuity there that's you can talk about closeness and a type of distance induced, but it's not exactly the natural Euclidean one.
Gotcha. I guess the next thing I want to ask is just how to generalize from these results. So we have these results on my understanding is that both of the processes could be represented by hidden Markov models with like 5 or fewer states. In general, of course, processes can have like a bunch of states in their minimal hidden Markov model. How scared should I be of like, oh, maybe things are really different if you have like 100 or infinity states that you need to keep track of?
You should be excited, not scared.
Okay.
We can just go to the full thing. Like, what's the minimal generative structure for all of the data on the internet? Right? That's a large thing. It's a very large thing. It is way larger than the number of dimensions in the residual stream of even the biggest model. Like it's not even close.
Right.
So the natural kind of bottlenecks that exist in the strongest versions of artificial intelligence systems that exist today do not have the capacity to, in a straightforward way at least, represent the full simplex structure that this thing predicts, which means that there is at least one extra question about how does some compression must be going on. What is the nature of that compression? This is something we're like very excited at looking at now. And I think the main thing that I get from our original work, although all these things about like fractals and finding fractals and transformers, all of that is true, and these are good paths to go on. But the more general point and the thing that gets us excited is that like it gives us evidence that this framework that we're using to go about thinking about the relationship between training data structure, model internals, and model behavior works. And now we can start to ask questions like, what is the best way to compress into a smaller kind of residual stream than you really have? And so now we don't have space to represent the full structure. How do we do that? And we don't have an answer to that at the moment. But yeah, it's definitely like, I think one of the things we're very excited to get a handle on.
Yeah.
So,
and at least the experiments become clear once you have the kind of theoretical framework is like, oh, now we know where the kind of simple picture should break down and we can look there. So yeah, we are very excited to see like how things start to break down and how the theory kind of generalizes to understand more towards frontier models.
Yeah, I guess you've maybe already talked about this a little bit, but I'm wondering what next directions in terms of understanding, these mixed state presentations in transformers, or just generally applying computational mechanics to neural nets. What are the next directions you're most excited by?
There's an incredible amount that we're excited by, which is like, so we currently have, this team of the two of us and collaborators in academia and also more generally in the AI safety interpretability community. But we're like, we're really excited to create more opportunities for collaborations and scaling up because there's a bit too much. But let's get specific. There's some obvious next projects like the AI safety world's a little obsessed by SAEs, right? Sparse autoencoders. So
right.
and features. Like what even are they? Like how do we know if we're doing a good job? There's like no ground truthiness to it. And so one thing we're excited to do is just like, well, let's benchmark in the cases where we know like what the machine's trying to do, like that these are the optimal belief states. How do belief states correspond to features? And Adam alluded to this earlier, but one kind of working hypothesis could be that, features are these kind of concise minimal descriptors that are useful for pointing at belief states. Okay, so let's test that out. So we're doing a collaboration right now where we're trying to make this comparison. I think it's going to be pretty empirically driven for now, but But I think that that should be quite useful broadly to know what we're doing with features. There's a lot that I'm doing right now in terms of understanding internal representations more generally in a few ways. One is that so we have a lot of what we've done right now is like, what do you expect to happen once the model has been well trained? And then it's like, okay, it should have this structure at the end. But how should that structure emerge over training? And there's a few ways in which we have a handle on that, and something I'm very excited about. So I'm working actively on that. And we have a lot more. Do you have some favorites you want to talk about?
Yeah, there's actually, it's kind of a problem in that, like for instance, just last week, there was this Simons Institute workshop that had to do with AI and cognitive psychology. And I went and I watched a few of the talks, and this is something increasingly that's been going on with me. Not to get too personal, but like every time I see a talk about AI, often my reaction is like, I think we can like get a handle on this using our framework. So I just have like a list of papers that keeps on growing about like things I would like to explain from a comic point of view. But just to name a few of them, there's always in-context learning, which I think is a big one. You can start to think of a way to get a handle of that using kind of non-ergodic processes. So what that means is, in the examples that we've talked about in our public-facing work so far, the generative models are all kind of like single parts. There's like one hidden Markov model. You kind of go recurrently between all the states. Right. But you can also imagine processes where you just take a bunch of those and put them side by side. In addition to the beliefs having to kind of see more data and try to figure out in which state in the process you're in, you also have to figure out which process you're in. Right. So there's this kind of like extra meta synchronization process going on.
And it's natural also for the type of data that you'd be training on, because you have this whole hierarchical structure of what language, what genre, what mood, and they're like these kind of recurrent components, but many different recurrent components.
Yep. And you can imagine that dynamic being quite different for sets of processes which overlap in their internal structures more or less. And that might have implications for which types of which kind of abstract structures you use and take advantage of in in-context learning. Okay, so that's one thing I think we're quite excited about. Another one is kind of related to that, just talking more generally about kind of the capabilities of these systems and getting a handle. What is a capability? Like, what is the different types of computational structure a model can take? Because like one of the things that I really love about computational mechanics is it gives you a handle on kind of like, what does it even mean to talk about structure in these systems? Structure and training data, structure and model internal, structure and behavior. So for instance, and this is probably coming from kind of my neuroscience background a little, but like, what do we do in neuroscience when we want to study some cognitive capacity, like abstraction or transfer learning or generalization? Well, we want to run our experiments on like model organisms like rats and stuff like that. So what we try to do is we try to find the simplest toy example of abstraction, something that like has the flavor of abstraction in its minimal form that we can train a rat to do. Then we can go into the rat's brain while it's doing this abstraction task, and we can kind of do the neuroscience equivalent of mechanistic interpretability on it. So that was like my life for a decade. We can, if we can take abstraction, if we can find kind of a form of an abstraction task in the form of these kind of HMMs, and I think I have an idea for one. Now we can kind of say, like, for instance, let's say you have two generative structures next to each other, and they have the same hidden structure, except they just differ in the vocabularies they speak in. Right. So let's say one speaks in A's and B's, and one speaks in X's and Y's. Now, when we look at these as humans, it's very obvious that they have the same hidden structure. They have the same abstract structure, but they speak in two different vocabularies. What would it mean for a transformer to understand that these two processes have the same abstract structure? Yep. So if you train a transformer on this set of tasks, one thing it could do is learn them both optimally, but not understand that they have the same structure. Another thing it can do is learn them both optimally, but understand they have the same structure. Behaviorally, you could figure out the difference between those two cases if you test them on a held out prediction task, which is combining histories of A's, B's, X's, and Y's together in just holding the abstract structure constant. And if they can still do the optimal prediction task, now combining past histories of the two different vocabularies that they've never experienced together before, then you can say they've abstracted. In addition, because we have a theory for understanding how the model internals relate to any kind of behavior, we can make a prediction of what would underline that abstract structure. For each of the processes, for each of the generative structures, there should be a simplex geometry that's represented in the residual stream of the transformer. And the prediction would be that if the network is able to abstract and understand this abstract structure, then these simplex structures will kind of align in space, whereas if not, they might lie in orthogonal subspaces.
Okay.
And now all of a sudden you start to think of like the relationship between compression. If the residual stream doesn't have enough space to represent them in orthogonal subspaces, maybe it has to put them in kind of overlapping subspaces. And that kind of, you start to realize that there might be a story kind of in general, right? Like we were talking about before, in the real case, we don't have enough space to represent the full structure. So you have to do some compression. And because of that, you might have to, the network's kind of forced to take these, what should be separate simplex structures, and kind of overlap them. And that might be the thing that gives rise to out of distribution generalization and kind of abstraction and stuff like that. So that's another thing that I'm quite excited about.
Sure. I guess I'd like to move on a bit to the story of how you guys got into this, if that's okay.
Sure.
Maybe I'll start with Adam. So my understanding is that you have a neuroscience background.
Yeah.
Based on what I know about neuroscience, it's not predominantly computational mechanics, and it's also not predominantly saving the world from AI doom.
Yeah.
How did that happen for you?
Just last year, even, I was kind of towards the end of a postdoc in neuroscience, in experimental neuroscience. So I was, like I was saying before, I was training rats on tasks, and I was studying kind of the role of expectations and predictions in sensory processing and in visual cortex of these rats. And actually, I remember, running the experiments on these rats, and it was like a week after ChatGPT came out, and I was talking to ChatGPT, and just really shocked, I think is the right word, by its behavior, and just kind of like, just had a moment of like everything, all of my beliefs and intuitions for what I thought must underlie intelligent behavior were just proven to be wrong. I guess I had all these intuitions that kind of came from my neuroscience background about recurrence and complicated dendritic structures and all kinds of details. And I was like, there's some secret sauce in neuroscience that has to underlie intelligent behavior. Meanwhile, I'm studying these rats on these very simple tasks that are like basically not much more than left-right. That's kind of simplifying it and strawmanning it a little bit, but they're not super complicated linguistic tasks that humans perform. ChatGPT, after learning about the transformer structure, being like, these things are feed forward. They're weirdly linear. Like, they're not totally linear, obviously, and that's important, but like, they're much more linear in kind of its structure. Basically, to whittle it down, I was like, the architecture is not interesting enough to give rise to these interesting dynamics, given what I think about the relationship between mechanism and intelligent behavior. That was like kind of a shocking thing. And then also kind of realizing that like the existence of this system pushed more on my intuitions about intelligence than like basically any paper I had read in neuroscience in a while. Yeah, so it's a lot of like it's actually like emotionally a little difficult, I have to say. But yeah, at that point is when I started kind of thinking about that transition and like, if my intuitions are wrong about this, then what that means for the future. GPT-4 came out not long after that, and that was another like, whoa, okay, apparently it wasn't just this one thing. Apparently it can get better, faster. So yeah, that's when I started going. And there's always like some tension here, like kind of when you realize the safety implications for the future. And then on the other hand, it's like also just actually interesting, like literally just a very interesting, just intellectually super cool. And there's this like tension between those two things that I feel quite often. I'm pretty sure I'm not the only one in the AI safety community that feels that. But even from like my academic interests, like I'm interested in intelligence. I'm interested in the mechanisms that underlie intelligence. I'm interested in the way that networks of interacting nodes can give rise to interesting behavior. So yeah, I guess that's like the way that I found myself in AI safety. I guess the other relevant thing is for a long time, like 8 years ago or something, I had randomly run into CompMech as a neuroscientist, just kind of reading one of the papers. It just struck me, not that I understood it at all. I did not have, and I still don't really have the mathematical acumen to like grok all of its complexities, but something about the framework really captured exactly what I was interested in getting at in neuroscience, which had to do about this relationship between, what is the relationship between a dynamical process and the computation it performs? And so for a while, I would annoy all my neuroscience lab mates and stuff about CompMech, and I probably sounded like a crazy person. But I was never able to like really figure out how to apply it in any useful way. So yeah, I'm super excited to start working on these neural networks and applying them, like actually getting somewhere with. It's like an amazing feeling. Yeah. I'm very lucky to have met Paul and the other CompMech folks that are helping me with this. Yeah.
Yeah, maybe. Yeah, first of all, actually, how did you get interested in computational mechanics just to begin with?
Yeah, that goes back a long time. So I don't know if I can remember. I guess, oh God. So I have a background in physics. I've done theoretical physics. I also did a master's in electrical and computer engineering, but then was back to theoretical physics for a PhD. I was interested in emergent behavior, complexity, chaos, all this stuff. I mean, who isn't? But I think early on, like in let's say 2005, I had Jim Crutchfield as an undergrad teacher at UC Davis, and I just thought the stuff he did was super cool.
And he does computational mechanics?
Yeah. So yeah, he's been kind of the ringleader. It's been like Jim and colleagues building up computational mechanics. And I just like, so I guess from that point, I like realized what Jim did. I had some idea of computational mechanics, and I guess I was like going on a trip with my buddy, and my buddy Seth is like, well, what would you do if you could like do anything? And I was like, oh, well, I'd probably do this computational mechanics stuff, but like, I don't know if I'm like smart enough or something. But then, okay, turns out, you believe in yourself a little bit, you can do lots of things that you're excited about. I ended up, kind of long story short, doing a PhD in Jim's group. So I did a lot of computational mechanics during my PhD and have done a bit afterwards. But in physics, I've worked on kind of all sorts of things, been a big mixed bag of like quantum information, ultimate limits of prediction and learning, which is a lot where the CompMech comes in, non-equilibrium thermodynamics, but trying to understand just like what is reality like. So that's kind of my interest in CompMech was because it was very generally like what are the limits of prediction and learning? That seemed fascinating to me. maybe you have this follow-up question of like, so where, how did I get into some AI safety stuff, right?
Truly a master of sequence prediction.
Yeah. I felt very unsettled, a year more ago, with just what I was seeing in AI, like generative images, ChatGPT, this stuff. And I was very unsettled by it, but I also didn't think I had actually anything to contribute. Like actually when we would talk in Jim's group about neural networks, even it's back 2016 or something, it's just like, this stuff's so unprincipled. Like they just don't like, they're just cramming data into this architecture. They don't know what they're doing. Like this is ridiculous. So like, it was always just like, let's do the principled thing. Let's do CompMech.
Right.
So I think somehow this was just in my mind, like neural nets are the unprincipled thing and I do the principled thing, but now these unprincipled things are like becoming powerful. Like, well, what do we do? And it was kind of out of the blue that this guy, Alexander, like Oldenzeil, reached out to me and he's like, oh, CompMech's the answer to AI safety. And I was like, well, no, I know CompMech, you don't. You sound like a crazy person, but I do care about like, I already was concerned with AI safety. So I'm like, okay, I'll hear you out. And so I explained to him why it wasn't going to be useful. And, for example, like that these architectures were, as far as I understood them, that they were feed forward. Computational mechanics was about dynamics. And but we kept talking, and actually he did convince me that there's something about thinking about the dynamics through context, which is really important. And I don't think Alexander quite made the case for how they're important, but somehow I realized like, oh, this will be important. And actually at that point I started talking to Adam. This was almost a year ago, I guess, where Adam then started helping me to understand more of the details of transformer architectures and this stuff. And we were talking with Sarah Marzan and others, and started to realize like, okay, actually this will help us to understand model internals that people just aren't thinking about. It's going to help us to understand behaviors people just aren't thinking about. And so then when I realized that like, oh, there's actually something here, it felt both research-wise super exciting, but also like kind of moral imperative. Like I care about this, I need to do something about it. So I started just like reaching out to like, I don't know, people at Google or whatever connections I had and be like, hey, I feel like I have something really important to contribute here. How should I go about this? And the broad community of, interpretability in both industry and outside, people were very helpful for directing me towards, hey, there's this thing, MATS, which I don't know, maybe it's too junior for you, but actually for me, it was great. So I was a MATS scholar beginning of this year. For me, it was great just being surrounded by people that really understood the ML side, because hasn't been my strength, but now I've grokked a lot of that. Right. And so I'm really grateful that there has been a community that just cares about this stuff. And so many people like with Pibs, Nora and everyone, like so many people have just been asking, how can we help you? And that's been really cool. So Adam and I have been talking for a while. We've been working on this stuff, and I think earlier in the year, we were saying, this stuff's going really well. It seems like we have a lot to contribute. At some point, like, we should maybe do an organization on this, research organization. And so we were open to that idea. And then kind of things fell in place where it's like, oh, I guess we can do that now.
Yeah, I'll second the thing that Paul said about how supportive the broad AI safety community has been. So for the last 6 months, I've been a PIBS affiliate, and that's another AI safety organization, and they've been really helpful to both of us, I think, kind of supporting us in starting Simplex and the research and everything.
Sure. So I think I understand your individual journeys. One thing that I still don't quite understand is how did you guys meet and sync up?
It's this Alexander guy again?
Yeah, yeah, it is Alexander.
This is the second episode where
right,
Alex cold emailing people has played a crucial role in someone's story.
Some wizard in the background.
Yeah. Well, I met Alexander, it's probably almost 2 years now ago, at some rationality event thing that I actually wasn't even invited to. I was just tagging along.
Okay.
I think, yeah. We started talking about rats and minimum description length things, and I was like, oh, that sounds like a less principled version of CompMech. And then I started ranting about CompMech, and then me and Alexander kept on talking about that and trying to think of if there was a way to apply it to neural networks. I had exactly the same reaction, like, I don't know, these aren't recurrent, so I don't really know how they would be relevant to transformers. And then I think after that, a little while after that, Alexander reached out to Paul, and I was having like a very frustrating day with the rats, I think, and I was like, I really want to do CompMech. I'll message. I messaged Sarah Marzin, and we had a meeting. It was really great. And then eventually all four of us got together and started trying to think of ways to apply CompMech to neural networks.
Yeah. So we were like on the side of, me and Adam were still both in academia. I was actually about to take on something that would have led to a tenured role at a university in Spain. We were looking forward to sangria, all this stuff. But we were just, we were starting to do this research on the side, and it was just like, was this thing. It was starting to go well, and we realized well, for me, I realized like, oh, okay, I need to dedicate myself to this. And so I think from like for me, kind of first engagement of like, okay, let's apply CompMech to neural nets has been kind of in collaboration with Adam, and so it's been really a great, I think, complementary set of skill sets coming together, and I think we have a lot of shared priorities and vision.
Yeah, it's been super fun.
Yeah.
Awesome. So I have a question just about the safety application. So my understanding is that basically the story is have a principled understanding of what neural nets might be doing. Just get some tools to have a more principled way of saying like what's going on there, and hopefully just use that to feed into, like making them safe, making them, designing them the way we want them to be. Is that right? Or is there like a different plan you have?
Yeah, I mean, that's an aspect of it for sure. But I think for me, another important aspect is enabling better decision making. People talk a lot about like, what's your PDOOM or probability of this or that. Like, I feel like we understand these things so little. We don't even know what the support is. Probability over what? Like, we don't know what's going to happen. We don't know the mechanisms, everything. We don't even have a shared language. Like, there isn't science being done the way that I think it needs to be and at the scale that it needs to be. So I think computational mechanics can, maybe optimistically, but I think it can help to figure out what are the things that we're most confused about, how do we go about that, and build up some infrastructure. Like, and some of that will be at a low level, some of that will be a high level, and probably going back and forth between those. So I feel like understanding is very important in general to make good decisions. So yeah, I mean, one is like, if you understand well, then you could have new interventions. So that's one thing. And then the other one is you might understand well that this will go very poorly in any case, because now we have a more mechanistic understanding of why or how things would go good or bad. And that's this other part that I think is really important.
Yeah, there's a few other things that kind of are related to that. So just to take a very concrete example, like, why don't we have rigorous benchmarks for SAEs? Why don't we have a data set where we know, or transformer, a combination of both, where we know exactly what the correct features are, so we can tell whether or not kind of a specific form of SAEs is like, specific architecture and losses and stuff, whether it works better or worse than other things. And I think it's because like we don't have an understanding for a lot of the basic concepts with which we talk about a safety relevant things like features. Like in this particular case, it's features. And the hope is that if we can get a better understanding, that we can even do things like build benchmarks, like a pretty simple thing. I think this also carries over to things like evals, right? Where if we had a better understanding of what fundamentally a capability was, like what are the different types of capabilities that we could hopefully also kind of build better evals. We can make And we can relate any particular eval that exists right now to kind of things going on inside of the transformer. This kind of also relates to things like out of distribution behavior. If we can relate the behavior in general of some internal structure in a transformer to all of the things it can do kind of as it spits out tokens at the end, then we will know kind of the space of out of distribution behavior. And nothing comes for free, right? It's an enormous amount of work, and it's not like a simple thing to go from kind of this theoretical understanding we have right now to kind of the application to the largest models that exist. That's not the statement, but at least we have like some footing here. So yeah, that's, I think, kind of the idea.
And just one more thing I'd want to add on this is there's a lot of power in CompMech in that the theory is model agnostic. Like most of the results aren't actually about neural nets, which I was surprised it was applied at all.
Right.
And it's not specific to transformer architectures, whereas maybe some mechanistic interpretability stuff would be architecture dependent. So I think that's powerful. Like for any particular architecture, you can then back out the implications. But as architectures change, this learning should be able to change, be adapted with us. So I do think that's important.
Yeah, so that's one story about how computational mechanics could be useful. One obvious way to like help push this forward is work on computational mechanics. Join Simplex, or look at their list of projects and like work on them. I wonder if there are any like synergies with other approaches in AI safety that you think work really well with CompMech that like are good complements to it.
These connections haven't been made formally. I think there's like kind of an obvious connection to kind of mech interp in general, which is, I guess, kind of a big field. But for any kind of mechanistic understanding one has from kind of the standard tool set of mech interp. So these are things like looking at attention head patterns, causal interventions of different forms. One can ask now how these relate to the task of carrying out the mixed state presentation.
Yeah.
I'm hoping that there are synergies with kind of a more dev interp point of view. I think there's already there's a bunch of pieces of evidence that point that will work out. Right. We can see this kind of belief state geometry forming over training. Paul has theoretical work talking about the learning process of a parameterized model from the point of view of CompMech. So hopefully we can also connect this thing to the training process itself, which is kind of a dev interp, maybe SLT, flavored way of looking at things. I mentioned evals before. How many different AI safety approaches are there?
Unclear to me. So if I'm thinking about how computational mechanics does apply to safety, does like help things being safe. We've talked a bit about the theory, and it seems like it's mostly a theory of doing good inference about stochastically generated processes that, somehow, like, at least my impression is I'm imagining like, yeah, someone else is generating this process, I'm inferring it, and then computational mechanics is saying, okay, what's going on there? What's going on in my head? But if I think about AI, one of the crucial, important features of it is that it involves things acting in the world and changing the world, right? Not just inference, but like this whole loop of inference and action. And I'm wondering, like, are there developed computational mechanics ways of talking about this, or is this an open area? I think Adam mentioned, I forgot what word it was, but there was something about like computational mechanics with two systems that were maybe influencing each other. Yeah, is that enough? Do we need more?
Yeah, I guess I'd say there's some basically preliminary work in computational mechanics about not just what it's like to predict or to generate, but really putting this together in an agentic framework. There's, instead of epsilon machines, epsilon transducers, which is what's the minimal structure and memoryful structure for an input-output device.
Yep.
So that, I think, is really relevant work that Also, we can probably look at like model internals and things like that. But I think there's a totally different level at which computational mechanics can be applied that we're excited for, but just don't have the bandwidth for right now.
Right.
In terms of what to expect with interacting agents, like at a high level. There's a lot of ways to go about this. Like, there's theory work that's been done with, POM-DPs and, but I think that there is work that has been done in terms of basically these memorywful input-output agents. There's a lot to do. I indeed feel that's important for understanding, like, if there's any hope for understanding what the emergent behaviors of interacting agents would be. Sounds hard. I'm curious about that. Things need to be developed a lot more.
Yeah, I think just to add on to that, some of the things that would be exciting to try to get a handle on, conceptual things to get a handle on from that point of view, would be things like, what does it mean for an agent to understand some structure in the world? What does it mean in terms of its internal states? And then kind of going a level beyond that, what does it mean for a model to have, for an agent to have a model of itself in its inside of itself? And what is that kind of computational structure that subserves that? So I think these are like pretty fundamental questions that one can, the work hasn't been done yet, but one could kind of imagine using and extending the framework of transducers to kind of get at that, which would be super exciting.
Yeah, listeners, I guess, have now heard like the exciting promise of computational mechanics, like cool things they can do, cool things that work with it, cool, potential like threads of using it to understand agency. If people want to follow your guys' research, your writings, like how should they go about doing that?
I think the main way is simplexaisafety.com, our website. You can even contact us. We're very excited to kind of collaborate and work with other people. So if anyone is interested, they should certainly feel free to contact us through there.
Yeah, for sure. I'd say that people that feel like there's a natural connection, if you're feeling inspired to make our mission go well, or you see a natural collaboration, please feel free to reach out, because we feel like this work's really important, and we're just a bit bottlenecked. So I think working with good people and like growing a vision together would be really nice.
Great. Well, thanks very much for coming here today. It was great talking.
Yeah, thanks so much.
Daniel.
This episode is edited by Jack Garrett, and Amber Dawn Ace helped with transcription. The opening and closing themes are also by Jack Garrett. Filming occurred at Far Labs. Financial support for this episode was provided by the Long-Term Future Fund, along with patrons such as Alexei Malafeyev. I'd also like to thank Joseph Miller for helping me set up the audio equipment I used to record this episode. To read a transcript of this episode, or to learn how to support the podcast yourself, you can visit axrp.net. Finally, if you have any feedback about this podcast, you can email me at feedback@axrp.net.